Alright, now let me write out yet again the natural numbers, the counting numbers. 0, 1, 2, 3, 4, and so on and so forth. Now, I said that these numbers, each of these natural numbers, can be factorized, and that is to say, each of these natural numbers, we'll forget the 0 for the moment, each of the positive integers, as we say, the whole numbers which are greater than 0, have factors. That is to say, there are some numbers which, when multiplied together, equal that number. In the case of 1, well, 1 and 1 multiplied together give 1. In the case of 2, 1 and 2 multiplied together give 2. Is there anything else? No. In the case of 3, 1 and 3 are multiplied together to give 3. And is there anything else? No. In the case of 4, 1 and 4 multiplied together give 4. Is there anything else? Yes, as a matter of fact, there is. It's 2 and 2 multiplied together give 4, and so on and so forth. And these pairs of numbers, 1, 1, 1, 2, 1, 3, 1, 4, and so on, are said to be factors of the given number. Now, you'll notice that some of these numbers, 1 to 4, I'll just put a red line under them, 1, 2, and 3, only have one set of factors. And we call numbers which only have one set of factors prime numbers. Let me just write it out here. We've already just introduced prime numbers a little earlier. My writing is absolutely awful, so please forgive me. They're prime numbers. I keep saying my writing is awful, and I keep telling the truth when I do say it. Sometimes we write out we call them prime numbers. Sometimes we'll use the shorter expression primes, and the singular will be prime. So we'll say that, for example, the number 2 is prime. So prime numbers. Now I'm going to show something pretty cool, or at least the way in which I show it hopefully will be pretty cool. And what I'm going to show you is that every positive integer, that is, for any number, 1, 2, 3, 4, as far up as you like to go, to whatever number, any number has prime factors. So let me just write out what I mean here. I'm going to change color again. Any natural number, gosh, my writing really is even worse than I thought it was. Any natural number, well, let's call any old number m, has prime factors. That is, a set of factors all of which are prime. Now, how are we going to prove that that is the case? And let me just improve that m. There we go. A comma here, comma there. How might we prove that's the case? Well, you might say, well, one way in which we could try to prove it is to start at the beginning, check that 1 has prime factors, and indeed it does. Look, 1 and 1 here, and 1 is prime because it's got a red line underneath it, and 2 has prime factors, 1 and 2, and 1 is prime because it's got a red line under it. 2 is also prime. Same with 3. What about 4? Well, 4 is 2 times 2, so 2 is a prime number because it has a red line underneath it, and so on, and we could check all the way on up the line. Now, the problem with that might occur to you, and the problem is this, that there are an infinite number of positive integers, numbers in this sequence. So we might carry on checking each number for years, and we might say, well, all of them that we've checked so far have prime factors, but of course that doesn't show to us, it doesn't prove beyond any shadow of a doubt that there isn't some number that we haven't yet got to which doesn't have prime factors. And it kind of is like the guy who's falling off a huge mountain, or falling down a big cliff, which is sort of unfortunate, and he's thinking to himself, the further he falls, the more he thinks, well, so far so good. Of course, just because he hasn't hurt himself by hitting the ground so far, it doesn't mean to say that at some point in the future he isn't going to hit the ground. And in just the same way, because we check out all of these numbers and we haven't found one thus far which is not factorable into primes, it doesn't mean to say, it doesn't show conclusively that there is not yet one that we haven't yet checked that does not factor into primes. Now I'm going to show you, I'm going to prove about all the numbers that they are factorable into primes, and for that purpose I'm going to use a type of proof which we call mathematical induction. This is a proof by mathematical, my writing really is bad, induction. Now it seems pretty complicated, doesn't it, if you just take those words, but really once you explain it, it should be reasonably straightforward to understand. Now I say that despite the fact that I must admit that even some people who are quite advanced in maths, who are seniors in high school and even perhaps in college, sometimes have a little bit of a problem with mathematical induction. And if you're going to become adept, competent at mathematical induction, proofs by mathematical induction, there's only one way to do it, and that is to practice, practice, and practice. Alright, now let's just look at how we're going to prove this proposition that any natural number m has prime factors using mathematical induction. Well, let's take m, and we're going to assume, this is an assumption, we're not proving it yet. We're going to assume that any number, and let's call it n, which is less than m, and remember we have a sign for less than, which is a kind of V on its side like that, which is less than m, has prime factors. Okay, and that's what we're going to assume. And then what we're going to show is that if that is true, then m has prime factors. Now how are we going to do that? Well, let's assume that m, we know that all natural numbers have factors. Let me just change color actually to make this a little more straightforward. Let's assume that m has factors j and k. So m is equal to j times k. Now, either j and k are less than m, or one of them is equal to 1, and the other one is equal to m. So let's just take that case first. So case 1. That j, let's say, is equal to 1, and k is equal to m. So m equals 1 times k. Well, if they are the only factors of m, then m is prime. If they are the only factors, good Lord, look at this. My writing is getting worse and worse. The more I practice, the worse it gets. That isn't the way it should be, is it? If they are the only factors of m, then m is prime. And if m is prime, then it has prime factors, because j is 1, which is prime, and k is equal to m, which is prime. So let me just put a big check mark there to show that that's done. Now, case 2, the other possibility, is that both j and k, oops, again my writing is really going nuts, are less than m. Well, now, if they are less than m, then they are, by our assumption, factorable into prime numbers. They have prime factors. So that's by our assumption. So on that basis, let's assume that J has, on that assumption, J has prime factors, and let's call those factors P1 and P2, and that means that J is equal to P1 multiplied by P2. And of course K is less than M also, so by our assumption it has prime factors, and let's call those prime factors, for example, P3. I don't know what these P3, P1, P2 are, they're just prime numbers, and P4, and let's say it's got another one as well, multiplied by P5. So those are all prime numbers because those are the prime factors of this J and K. Well, in that case, given that M is equal to J times K, we know that M is then equal to P1 times P2 times P3 times P4 times P5. In other words, P1, P2, P3, P4, P5 is a set, together constitute a set of factors of M, because multiplied together they equal M, that's what factors are, and moreover they are all prime numbers, so M has prime factors. So in that case too, let me put a check mark here, M has prime factors. Right, now let me just continue on a fresh sheet of paper. So, what we've shown so far is that taking the positive integers, we have 1, 2, 3, and so on. And then we get to one which is J, and then we get to another one which is K, and then we keep going up, and then we get to another one which is M, and so on and so forth. And we know that if all of these numbers less than M have prime factors, then M does. Then the next one. If all the ones before it in the list have prime factors, then it does. Now, how can we use that fact to prove that all the numbers in the list, wherever on the list they appear, no matter how far out here on to the right they might appear, how can we show that all of them have prime factors? Well, all we need to do now is to check that the early ones, the ones at the beginning of the list, do. Well, 1 does, because 1 is 1 times 1, so that has prime factors. 2 does, because that's 1 times 2. 2 itself is prime, of course, so that has prime factors. 3 is 1 times 3, and 1 and 3 are prime, and so on. Now, if they do, because we've just shown that if all the ones before any number in the list have prime factors, then that number, the number that immediately follows them, has prime factors. Well, in that case, 4 has prime factors, and because all of those do now 1, 2, 3, and 4, so does 5, and because all of those do 1, 2, 3, 4, 5, so does 6, and so on and so on and so on, right the way along the line, no matter how far you care to go. And that is what we call a proof by mathematical induction, and I hope you'll agree it's a pretty cool way to prove something, isn't it?